Today we're going to learn about the mole. And the mole is essentially our connection between the submicroscopic world of atoms and stuff that we can actually measure like mass in grams. So a mole of any substance weighs its average atomic mass in grams. And as we learned before, the average atomic mass of an element has to do with its basic nuclear components. So for example, hydrogen has 1 proton typically, so we'd say its average atomic mass is 1 atomic mass unit. Carbon is 6 protons, 6 neutrons, so it typically has an atomic mass of 12 atomic mass units. And sulfur, 16 protons, 16 neutrons, it would have an average atomic mass of approximately 32 atomic mass units on average. Now, if we take those atomic mass units and convert them to grams, that's essentially a mole. So a mole of hydrogen weighs 1 gram. And we've calculated that in that 1 gram of hydrogen, there would be 6.02 times 10 to the 23rd atoms, which is an unfathomably large number. Think about that. A billion has 9 zeros after it. That's substantially more than that. A mole of carbon weighs 12 grams because of the 12 nuclear particles on average, and that would also contain that same exactly large number of atoms. So different elements have different masses per atom, and therefore a mole of them will weigh a different amount. Sulfur, as another example, weighs 32 grams per mole, and that would also contain 6.02 times 10 to the 23rd atoms. And the reason this is important is because when chemicals react, and that's what chemistry is, it's the study of reactions, matter, and the changes it undergoes, things react relative to the amount of atoms that go into a product. So this is just an example of a reaction. We have carbon reacting with sulfur to produce carbon disulfide, and they react in a 2-to-1 ratio. However, by mass, it's not 2-to-1. You just can't take twice the weight of sulfur as the carbon and put them together and get the right amount of product. Things react in mole ratios, which is based on the number of particles, not mass. So we need a way to be able to convert from the particle world to something we can measure in the lab. So in this example, if we were making 1 mole of carbon disulfide, you'd use 12 grams of carbon, and you'd end up using 64 grams of sulfur. More than 2-to-1 as a ratio, and we would get a total mass of 74 grams. Law of conservation of matter. Matter is not created or destroyed. If everything went perfectly well and we got 100% yield, you would have the same mass product as you did reactant. So, taking a step back, that's what 1 mole weighs. So if we have 2 moles of a substance, it's going to weigh twice as much and contain twice as many particles. And if we had half a mole of it, we would have half the mass and half the particles. But we can use these, it's basically a conversion factor. 1 mole relative to the number of atoms is a conversion factor we can use in order to do these calculations. We also have the conversion factor that's here of the moles of that element and how much it would weigh. So essentially, if we're going from the grams that we have of a substance to try and find out how many moles we have, we divide by the average atomic mass, give us the number of moles. If we then wanted to go further and figure out how many particles that would be, we would then multiply by Avogadro's number to figure out how many particles we have, whether it's atoms, molecules, or anything really, as long as that's what we're describing. We could also go the other way. If we knew how many particles of something we had, we could figure out how many moles we have, and then we could figure out how much that would weigh. So a couple types of sample problems you might get would be, if I ask you, how many moles of carbon are present in a 6-gram sample of pencil lead, which is really graphite, which is pure carbon. So we know from earlier that carbon weighs 12 grams for every mole. So if I have a 6-gram sample, and there's 12 grams per mole, I have half a mole of carbon. And it's crazy to think that we can actually now quantify how many atoms of carbon that actually is. So if you have half a mole of carbon, and each mole contains Avogadro's number of atoms, then we have 3.01 times 10 to the 23rd atoms of carbon in that box of pencil graphite.